So my name is Brian Wilt. I'm a software architect on a product that we overarchingly call QuickAssist. It's our Intel QuickAssist technology. It has many instantiations, and I'll go through those. So my hope is at the end of this, you'll have a good understanding of what QuickAssist is, and it'll be very visible as to how it can get used in a more practical terms in real-world kind of applications. So QuickAssist is an accelerator. It's got a number of different instantiations physically, which I'll show you in the next slide. But roughly, its acceleration components are cryptographic ciphers and authentication, asymmetric cryptography or public key cryptography. This is actually a build. So that's going to be all your session establishment work. So anytime you connect to an SSL web server, anytime you create a new IPsec terminal, that's your PKE or public key cryptography, asymmetric digital signatures and key exchange. And then finally, compression. And compression is an interesting one because it's got two facets. Most of this stuff came from a networking security background, but this also has a large component in the data storage space. So I'm going to go into both the networking side of it and some of the data storage. And as everybody probably knows, even in the networking space, there's a large storage component to that. So I'll be trying to tie all that together. Now, this is its physical instantiation. So QuickAssist comes in kind of three different flavors. It's an accelerator. It's connected over PCI. It can come in as a chipset. So you can buy a chipset with QuickAssist capabilities built into the chipset for your standard server platform. And you'll have various SKUs of that will give you different performance envelopes, which we'll look at in a minute. And you can buy a completely adjunct PCI Express card. There are vendors who are producing these today. You can go out, you can buy one, again, at different data points or at different throughputs. Mainly tailored around bulk crypto throughput, PKE throughput, usually RSA-2K, because that's kind of the most popular key exchange mechanism today, at least for SSL, and elliptic curve. And then compression throughput on that card. Again, these are all connected over PCI Express. And then we've got the SoC form factor, or the C2000 class, which is our Atom class SoCs, which actually have QuickAssist built in to the SoC itself. So there's a lot on this slide, but you can think of this as a very quick data sheet on the performance and features of the bulk crypto, and I believe this has the asymmetric crypto on it as well, sides of Coleto Creek, which is our Gen 1 device. That's the one that's in the market today. You can go out and buy cards, chipsets, and the SoC is a different product. That's the C2000, and that's a different performance envelope. So the main target models for the crypto space is really IPsec and SSL. It's both in the bulk transfers for both of those protocols and the key negotiations. Primarily the SSL is going to be the key negotiations because that's the heavyweight part of the SSL portion. IPsec is going to be the bulk transfers because you usually have very long-lived connections in the IPsec space. As you can see, we support a host of kind of standard crypto algorithms. The ones that are going to be kind of popular today in the SSL space are going to be your AES paired with SHA, usually SHA-1 or SHA-256, AES 256 or 128. Or, and in the kind of the asymmetric case, you're going to have RSA, or kind of the new, not that new, kind of in the last 2 years, things have moved to what's called PFS, which is perfect for secrecy. That is usually it's implemented as a combination of elliptic curve Diffie-Hellman with the E is where you get your PFS from it. That's your ephemeral key. So essentially every time you create a new connection, you also create a new key as part of that transfer. And that way you get the PFS capabilities, which means that if somebody were to hack, say, your certificate, they can't go and decrypt all of the connections. They can only spoof as you. They can't go back. In the old days, no, not the old days, there's still a lot of RSA-2K certificates out there. But if they got your private key of the RSA-2K, they could actually, if they were sniffing all the traffic, they could go back and decrypt all of those connections. Whereas with the elliptic curve Diffie-Hellman ephemeral, you can't do that because it's a new key each time. And you can do this with Diffie-Hellman ephemeral, but it's actually faster using the elliptic curve transforms rather than raw Diffie-Hellman. And that's usually paired with RSA-2K for the signature portion of it, or it's paired with ECDSA. Then we go into kind of our authentication modes, and again, typically, your authentication is always going to be paired with one of your bulk ciphers. So that's either going to be done with AES-128, CBC, HMAC SHA-1, or it's going to be done with something like AES-GCM, which has both authentication and bulk encryption as part of it. And then, kind of as we already saw, we've got your RSA-2K and elliptic curve. So that, as you can see, we kind of have the gamut of your most popular and then your wireless transforms like Kasumi, Snow 3G. So we kind of cover all the well-used crypto algorithms, the ones that are very much used in the market. To put kind of real-world numbers on it, so if we look at like TLS at 4K record sizes, and TLS kind of varies, the average record sizes are going to vary depending on the implementation, is going to vary between 2K and 16K. The protocol lets you do a 16K. Some of the websites that want more responsiveness will force that down to a lower record size, just from a responsiveness standpoint. For 4K record sizes, we can push that up to 50 gigabits per second. And later on, I'll show you a set of benchmarks that show in an actual web server where we can drive these different performances with Quick Assist. IPsec at 512 byte packets, again, 50 gigabits per second. Public key encryptions. So if you look at an RSA-2K and you take your RSA-2K certificate, we can drive up to 40,000 operations per second. What you can also do, or what you can take that as, is we can also do 40,000 SSL connections per second. And I'll show you later data points where we have a web server running at 40,000 connections per second and how many cores it takes to drive through a full Linux system. Same with the PFS and the two variants of PFS, RSA-2K and ECDSA. And then we've got our wireless ciphers pushing at 20 gigabits per second. And again, this is for our Gen 1 device, and then cipher a hash only. And this is really looking like if you want disk encryption. Again, this is a device that provides acceleration of crypto and compression, so its usages don't have to be tied to just networking protocols. It can be integrated, and you'll see that later on with some of the compression stuff we've integrated into other things like storage.
Brian only talks in abbreviations and
yeah, so
acronyms. So
TLS.
Let me know if I'm saying something that isn't obvious. So if we go to the data compression side, so the data compression that we provide is deflate standard. So you can take your off-the-shelf zlib, go to zlib.org, download it. That's going to be deflate. The format that we produce out of the accelerator is fully compliant with that standard. You can take zlib, you can compress, we can decompress, we can compress, you can decompress with zlib. So it's fully compliant to that. The usage models are going to be kind of your big data applications, WAN acceleration, which is where this technology kind of came up from, IP comp, and general WAN acceleration techniques, HTTP compression, file system, and databases. That's kind of the ones that we've done work on, and we've done integration work on, and you'll see later how we've hooked some of this into the different frameworks. It supports a number of different features around compression, and if you look at compression, your features are really bound to, do you want better compression ratio or do you want more speed? Everything you tweak around a compression algorithm is going to drive one of those two. If you want better compression ratio, you usually almost always have to give up speed, and vice versa.
Have you done any performance benchmarks where you're stacking up security and compression in the same data stream?
We have. I don't have numbers here for that, but mainly what we've done that for was HTTP-based compression with SSL underneath.
Yes.
And what we also support is this concept of chaining. So in one request down to the PCI device, you can actually compress and encrypt.
So yeah, in one operation, so I can send it through the Quick Assist and come back with both done.
Yes, so it's one traversal over PCI Express, and we push that really for the storage type use cases where you're going to do block-based compression and encryption of that data. So again, what you get back is you get a fully compressed and encrypted block that you can then just push directly off to the block.
Well, or for SD-WAN, if you're trying to do WAN acceleration over IPsec or something.
Yep, exactly.
Cool.
So we have this, what we call our chaining mode. The other version of that chaining mode is that you can also do hashing. So if you, like a dedupe system where it needs signatures of each of the blocks, we can use like a SHA-512 or a 256 based hash to give you the signatures as each of those blocks are being compressed. And then we also have this other thing, compress and verify. So again, depending on the level of your system, it'll actually do verification of the output data blocks from the compression piece. In current generation, it's a 24 gigabits per second. We spec that at level 1 using Calgary Corpus. We set the configuration parameters so that it's comparable to zlib level 1 compression ratios, and we use the Calgary Corpus and Silesia to spec that out at 64K chunk sizes or buffer sizes. Our performance brief has a lot more data in or around different packet sizes and different pieces, but that's kind of how we summarize it up. So what I'm going to try to focus on now is the enablement pieces of it and how you can use and the effort that you have to put in to use Quick Assist. Again, it's PCI connected, but what we've been doing a lot of, and what I've been doing a lot of lately, is over the last number of years, is trying to make this as seamless as possible to fit into standard applications that would be used in the market. So if you look at like our operating system support, we're in the mainline kernel, Linux kernel today. Quick Assist driver is there and capable. You download, you'll get, at the moment, you'll get all the bulk encryption capabilities. You also get some of the PKE. You'll get the PKE through LKCF. We're also actively contributing to the Linux kernel to expose things like compression and other, say, elliptic curve transforms that LKCF, say, wouldn't have supported because a lot of that PKE stuff would have never been done in the kernel before. That actually has a knock-on effect from a storage perspective because all of your storage block devices are usually going to be driven from the kernel. So exposing compression out through LKCF also gives us the ability to do transparent integration into those storage drivers. We're doing work on both Windows and FreeBSD, and we're looking at the enablement of Quick Assist into that, and we're active in both those spaces. Hypervisors, so KVM, SRIOV we support. We're doing work on VirtIO in that space. Again, doing work on VMware and Xen, and then exploration from a Xen perspective is on VirtIO. libvirt and Docker we support. OpenStack we're investigating. We've done a lot of work, and you'll see later on. I've done a lot of work on this, and that's why you'll see a lot about this later on in the slides on OpenSSL. So if you have any questions on OpenSSL, I can go into a lot of depth on that or on zlib. And then Linux kernel crypto framework, as I was mentioning, we've been supporting what's in the LKCF framework, but we've also been expanding that out to support the other transforms that we support from a crypto perspective and from a compression perspective. We're adding a unified kind of compression API with the Linux community, of course, to expose out the compression capabilities. Applications. So this is where, and this is where I spend a lot of my time, is what we saw on the previous slide is the base set to expose up all the capabilities of the device. What we're seeing here is where we take that into a full-scale application and start to do benchmarking, start to do performance tuning, and figure out, does it fit into the typical framework models, and what do we need to do to fit that into the framework models. So today, with changes that we made in OpenSSL and upstream to OpenSSL, we support Nginx. And that's going to be out of the box. We're working on getting changes into Nginx so that it supports the new version of OpenSSL that's coming out, OpenSSL 1.10. OpenSSL 1.10 is going to have a full asynchronous framework built into it, and we worked with OpenSSL to get those capabilities into the main line of that stack. Nginx can be used as a reverse proxy, but we've also looked at using like HA proxy as a reverse proxy as well, and we've done some investigation on that. Again, it's in development, and we don't have that released. And the ADC space, we're aware of Squid. We've done a little bit of work on it, but again, it's a matter of getting that work done. Linux Netkey is natively supported because we're now in the kernel, and we support LKCF. Parallel file compression, this is the utility we built, and some performance optimizations around what you can do with compression if you do some tweaks to how you change your block sizes. So again, this is a piece of hardware that has a number of processing units underneath inside the device. So if you can parallel the blocks that get pushed into compression, you can also parallelize the job, and you can drive the data rate. And again, if you look at storage, that's a very transparent use case from a storage perspective because they can present to you a large number of blocks that you can then go compress in parallel. But again, the frameworks aren't used to doing this because they're doing everything sequentially. So we then go into these frameworks and we try to upstream patches to get both asynchronous capabilities, optimizations around memory management, optimizations around data movement and amortization. Similar to what Keith was talking about around the DBTK, we try to push some of these into the main lines of these different open source frameworks. So file systems, so BTRFS, we're on track to upstreaming that work. Seekable compression, that comes from some of the chaining stuff we talked about before, and the batch and pack, which is a feature that we have inside Quick Assist. And then chaining is in exploration, but we've done some work on that internally. The big data, we've got a codec available for Hadoop for compression. And I'll show you slides later on where inside the Hadoop framework the compression kicks in with respect to this. And then we're investigating Apache Spark today.
I'm sorry. On the chaining, when you're talking
that focuses on storage. Are you looking at like ext4, Btrfs, ZFS? I can throw out all the various file systems, like embedding that support for using the offload. Thinking more along the lines of leveraging what you've done for somebody to come up with a new pair of controllers for the next storage platform.
Both. So it's a kind of a path forward. So and maybe not exactly the last point that you made, but so Btrfs is a good example. Btrfs by default supports compression already. I don't think by default it supports encryption today. They're adding that in. So in order for us to get chaining support into that, we have to essentially upgrade Btrfs to start supporting encryption, get that integrated into the Linux kernel so that it has a uniform, it hooks into the LKCF inside Btrfs. So our first step with Btrfs was just to add compression. With other customers that we work with that aren't based, they have their own storage file systems, they have their own stacks, we would work with them on the chaining pieces and get chaining added into those. But that's because they have their own proprietary stacks. They can move the code around so that the encryption and compression are done in the same place. With a lot of these other stacks, they wouldn't have both of those capabilities, and especially not in the same place in the code where we can actually grab those as two operations. So we've got to work with them to try and bring that in. So I kind of see it as a roadmap that we work both with kind of the vendors that would build storage devices and can already take advantage of these capabilities. And then we would also work with the upstream to try and add these capabilities in one at a time. Usually compression is the first to get in, and then encryption from a storage perspective.
And if I recall correctly, Btrfs does check something at the block level?
It does.
Can it leverage Quick Assist? Sorry.
Not today, but that's becoming a feature that we're looking at, put it that way.
Okay.
So part of this as well is us learning what becomes a valuable piece of that picture as we start to integrate into these applications. We find new things that we wouldn't have expected to be performance problems as we start to integrate them in. And once we do that, we can add those capabilities.
Pushing the bottleneck around.
Exactly. Once you get rid of one, another one appears, and we start to look at that. And actually, that was like even in the SSL space, I did a lot of work on SSL and tried to get our acceleration technologies working with OpenSSL and with Apache. And I quickly found out that the parallelization that we have is hard to use in the standard framework because you don't have asynchronous capabilities. You only have synchronous. So then we worked with OpenSSL to add full asynchronous capabilities into the stack, and that it can take advantage of it to try and get rid of that bottleneck. And then we're also doing similar work on RocksDB and MongoDB, and a small bit of investigation we've done on MySQL, but these are kind of the two more mature ones that we're looking at today. So from an actual product standpoint, if we look at the compression side, these are just some quotes and products that are in the market with respect to Quick Assist today. So the IBM Flash V9000 is already using Quick Assist from a compression standpoint. And then F5 have a number of products out with respect to Quick Assist. These performance numbers, I'll actually go into these in much more detail later on. These are our stack that we produce internally. So this is our full Nginx stack up, and these are the performance numbers that you can get with that. And essentially, if you look at like so this is with our previous version. So OpenSSL 1.10 hasn't been released yet. So we did patches that added asynchronous capabilities to OpenSSL 1.01. These benchmarks are based off of that. We're going to release the newer ones when the new stack actually becomes publicly available. Beta 3 is out, so we expect the final version to be released very soon. But the changes that we made in this stack are very, from a capability standpoint, are very similar to what's going to go into the mainline. So we'd be expecting that for RSA 2K operations, right now it takes 7 cores or 14 hyperthreads to get 41,000 connections per second using RSA 2K. And I'll show you some graphs later on as to what per core numbers you'll get using software on a Haswell-based system. So this was on a 52699 v3. And as Keith was showing before, DPTK natively supports CryptoDev, which natively supports Quick Assist, and also supports the ASNI capabilities. So there are points where For smaller packets, encryption may be better. Again, we're traversing PCI Express. It may be better to do some of those in AS. And then, again, there's a different packet size where it's going to be better to offload those. PKE is a heavyweight operation, so a lot of the time it's better to do it in an offload case, but there's trade-offs. So DPDK natively supports both, and you can make those trade-offs for the application that you're running. And again, it's all uniformed under this CryptoDev API. Again, this is kind of going into the CryptoDev architecture and the structure. So say if the IPsec sample app that's available up on dpdk.org, I believe, it would be using the Ethernet PMD or the EastDev interface to get down into the NIC that you're choosing on the platform to do the IPsec benchmarking. And it would use CryptoDev API. Again, the IPsec application would be written to these standard interfaces, but underneath the hood, it would use ASNI PMD, or it would use a quick assist polled mode driver. So again, you can build up applications using DPDK. You get all the packet movement and transfer goodness and data rates, along with accelerated crypto, and you have options around that. So this is where I get into the actual applications we benchmarked, some of the upstreaming work we've done, and hopefully this will translate closer into kind of more real-world scenarios that people will have seen. I can go into this in graphic detail, but I'll probably go over this quite quickly. This is the work we've done with OpenSSL. So this is adding the async infrastructure into OpenSSL. So if you think about it before, all crypto operations in OpenSSL were synchronous. You'd call the libcrypto component or the EVP layer of OpenSSL, and you'd wait until that operation came back because they weren't asynchronous operations with respect to the core processor. What we did was we changed that framework and we added, with OpenSSL of course, the OpenSSL team did most of this work. We were kind of showing how we did it. Basically we took that component and we added an asynchronous capability. Originally it was kind of called Fiber. Now it's called the job infrastructure inside OpenSSL. But it allows you to take any operation that goes through the OpenSSL stack and pause it. And once you pause it, it will jump back to wherever you started that job or that fiber and return control to the application to manage it. So inside the context of one process or one thread, mainly, I mean, you're going to get better performance if it's in the context of one process. You can then pause any of the individual crypto operations, jump back to the application, and it can do other work. And in other work in this case is pull a new SSL connection, start off the whole TCP sockets part of that, and then when you get to the crypto part, push it off. And these fibers can then be signaled back to the application using the standard event-based infrastructure, and that wakes up the application to start pulling the requests. Now, I'll show you real kind of world numbers on this and what effect that has. I believe it's in the next slide. Well, not in the next slide because I got to build up to what this benchmark is. So these benchmarks are reasonably, okay, from a real world application, they may seem a little bit simplistic, but again, we wanted these to be simplistic because they push the envelope of the different crypto capabilities. So in this specific one, what we have is two benchmarks. We have a server benchmark where we set up this device here as either a server or a proxy that's using Nginx, OpenSSL, and a standard Linux operating system with the Quick Assist driver and the Quick Assist device. And then over here, we use just standard software to make SSL connections. And that's done in two flavors. In the server-based one, it's done as connections per second, where we simply create a connection, we do a HTTP GET of 1 byte, and we close the connection. So what you're really doing is you're pushing the envelope on your PKE operations. It's not going to be real world. It's a denial of service attack. In a real world, there's devices that we build that fight against this. But this is just to show how many TLS connections you can actually create per second. The second one is the proxy, and that's where this device is simply terminating it's bridging the SSL connection, so it will do the decryption and recreate a connection on the back end. It's not terminating the whole connection, so it doesn't go through the whole key negotiation again. It just does mainly the bulk encryption. And in this one, so that the benchmark is very easy to set up. You set it up once, and to configure it for either the proxy or the server, you just change the request size. So the application data becomes either 10 meg, where it's going to be predominated by bulk crypto, or the application request transfer size becomes 1 byte. And then we go through the different certificate sizes. So the common ones that are used today, RSA2K, elliptic curve RSA2K, which is a P256 curve, our elliptic curve Diffie-Hellman, which ECDSA with a P256 curve, all on TLS 1.2. And then these are kind of your bulk transforms, AES-128 CBC SHA and GCM SHA-256. Now, this is probably the more interesting piece. Everything in green is Quick Assist accelerated. Everything in blue is a standard OpenSSL 102D or Beta 3. At the time when we were doing these benchmarks, those are the kind of performance points we were measuring them against. So if we take let's take a 1-core 2-thread, so that's the full core, right? The hyperthread that we use in this case is the one that's dedicated to that core. It's not off on a different core. So with Quick Assist, and this is again using standard OpenSSL, standard Linux, standard Nginx, with changes to be asynchronous capable. So we'd expect that all the main lines that we're putting in place are going to get similar performance. AES or RSA2K, you can do 7,500 connections per second with essentially one physical core. In software, you can do 983. So RSA is very CPU expensive. It's very cycle expensive. If we go down to the elliptic curve Diffie-Hellman ephemeral with RSA2K, that has an RSA component with elliptic curve Diffie-Hellman on top of it. Hardware is at 4,200 connections per second. Software is 838. And then you go down to the elliptic curve. Elliptic curve is cheaper than an RSA2K operation. Software can go up to 2,400. And hardware is at 5,400. So these are the tangible numbers that you should see if you deploy an Nginx web server today. And if you think about the number of SSL connections, like even if you look in the room, look at all the laptops, people probably have about 10 SSL connections open today, right now, between your laptop and your phone. Between the web searches are all now encrypted.
Probably
IAMs
more.
are all
I would
encrypted.
say more. I would say way more. I think on your phone,
I'm conservative.
on your phone alone, you don't even know, right? If you from Twitter to WhatsApp to Google to whatever, right? Whatever you have open in the background is
An SSL.
is an SSL connection, right? On your notebook, you probably we won't even know the amount of secure connections, even within every single tab. In Barb's favorite Internet Explorer, have every single tab might have a secure connection.
So this is assuming you're using a quick assist adapter.
Yes.
So if I have a single quick assist adapter, these are the numbers that I can expect. If I put multiple quick assist adapters, does
They scale.
next one? Okay, they scale up. Is it a 2x or is it?
So we've scaled up to on this particular device, we've scaled up to a quad.
And are you working with some of the manufacturers for a more of an embedded size card for some of the more proprietary form factors for that? Not just PCI?
We do design guidelines for whatever. So we provide layout guidelines in terms of like mini PCI or something like that. People can do it.
Yeah, I'm thinking blade server infrastructure where you have some kind of funky.
Yes. So we have people that are doing specific designs for their blade and rack deployments. And again, as Edwin was saying, we give out design guidelines because essentially this is a chipset that has PCI pinned out. So you can take that and you can do whatever design form factor you want. And we give out the design guidelines to build that however you want.
So if somebody wanted to build one card with 4 quick assist processors on it and make some massive accelerator, they could do that.
We have vendors that already do that, and that's in the market.
Okay.
I believe I have the names at the end of this, but you can actually go to certain vendors that are in the market today and buy a quad card. Now, the quad card is specifically, again, you then become PCI Express limited, right? And usually those are going to be Gen 3 by 8 devices. So you're not going to get full bulk throughput. You're not going to get full compression throughput of quad, but you'll get full PKE because the PKE operations over PCI Express are much smaller.
So at what point, how many cores can you go to before you have to go to a second card?
Well, so 40,000 is the cap for, we quote 40,000 as the cap for RSA2K operations. Measured, you can get it slightly higher, 41,000 at 8 cores. The reason we don't have quick assist beyond that is that Quick Assist, the single card implementation that we have here,
Oh,
doesn't
so
go
these
over
are all
40,000.
single card.
Yeah.
Oh, okay.
All the green here is single card.
Okay.
And I suppose that's the other point to mention. We cap out Quick Assist at about 7 cores. So if we take the comparable at 7 cores, software for 102D is 6,700. If we look at elliptic curve, that's a different picture. We cap out Quick Assist at about 4 cores. So 14,000 and 15,000. And that's because those operations are multiple operations to the card. It's 2 elliptic curve operations, and it's a ECDSA or it's an RSA. And again, software starts to get comparable for hardware kind of up around for the elliptic curve RSA, 18 cores. But for the 2 elliptic curves, it starts to get comparable at about 6 to 7. Our RSA is exceptionally computationally expensive. And again, all the software to replicate this is freely available. We have 2 Git repos, one that's targeting OpenSL 1.1.0, which hasn't been officially released yet. We also have what this benchmark was built on, our asynchronous stack that we developed on OpenSL 1.0.1.
And when you say 18 cores in that, you're talking about 18 cores on the Quick Assist card or 18 cores from the core?
18 cores from the CPU. So
from the CPU and the server?
Yeah.
Okay.
Yeah, so when I talk about cores here, I'm talking about the server cores.
Server cores.
This is using basically the capabilities of Quick Assist. So in the 1-core measurement, we stop at 6.6 because you're running a full stack. So the SSL stack and actually in this case, the kernel stack become the bottleneck, not Quick Assist. When we get up to the 41K, then you've hit the bottleneck as Quick Assist.
So the first 2, 1 core, 1 thread, 1 core, 2 thread?
Yep.
That's essentially just, using the hyper-threading capabilities. And again, because we added asynchronous, the reason we see a bump is that the cycles of switching give us the capability to drive Quick Assist harder.
Like 15% versus 10%?
Versus, yes.
I think adding the second thread, you get about a maximum 30% performance increase.
Oh, yeah, I was doing the comparison between card and not card.
Oh, right.
Yeah, so I mean, in the RSA case, you're at about, just under about a 9 multiplier. And it's different for the different algorithms. But for RSA, it's about a 9, 8 to 9.
So we mentioned these 3 specific ciphers. Is Quick Assist a more generic crypto acceleration in addition to those, or is that that's just the 3 you chose to test, presumably?
Yes. So these are the 3 kind of most predominant TLS public key algorithms.
And I know you said it's either a chipset or it can be on a PCI Express card. It's not necessarily the NIC, right? It's the chipset that's doing. So it's kind of the equivalent of, I guess what F5 was doing and A10 and companies like that with the load balancers, where they're putting on SSL hardware acceleration chips from Cavium and Broadcom, whoever else, to do that hard work. Would this kind of be a slot-in replacement, or is it more closely tied in with the CPU as well as a requirement?
Well, so F5 used this today. F5 used this in their products today, and that's what that previous statement was. But
I wondered.
But to answer your question, it is a discrete PCI Express device. Now, it uses some of the capabilities like DDIO of the CPU, and as a chipset, it sits alongside as a discrete device on the chipset, and it has its own dedicated PCI Express lanes up to the host complex, up to the PCI controller.
All right, thank you.
And that gives us the flexibility that we can have it as a form factor as a separate chipset, where it can stand alone as its own chipset, SoC, and the PCI Express.
Thank you.
And then we look at the kind of the bulk side of the picture, and this is the web proxy. This is using AS128CBC HMAC SHA-1, which was the predominant cipher suite. These are moving to GCM, but that was the predominant cipher suite, and it's still very popular today. And what you can see is, again, Quick Assist, again with the asynchronous capabilities, is essentially doubling based off. And again, this was done on it was done on the same processor as before, the 2699 V3. But you can see it basically doubling your performance of your bulk crypto. The second set of lines is kind of trying to represent some of the CPU utilization, because you get this effect where when you start to hit the cap of, and driving it through the application, we hit a cap of 40. That's a network cap rather than a Quick Assist cap. Quick Assist can go up to 50, but in this particular benchmark, with available PCI lanes, we had 40, essentially just over 40 capable of driving through the Linux kernel. So you start to see this effect where the CPU, because this is a measure of total CPU utilization, and the reason that line goes down is because you've just added 2 more cores. So essentially, you can see that as a flat. It just starts to flatten out when it starts to flatten out Quick Assist. It looks a bit funny on that graph, though. Okay, this is going to be fun. I have to wrap up, so I'm going to go kind of quickly through some of the storage pieces. So, looking at your question before BTRFS, BTRFS already supported zlib and LZO. We added a compressor for QAT. Our long-term plan is that we're going to add an LKCF compress in here. So it will use the in-kernel version of Quick Assist to do compression at a block level inside BTRFS, and we'll upstream that to BTRFS. And we have patches posted for both LKCF and BTRFS today to do that. Performance, again, because I'm kind of going quickly, what you will see in this benchmark, so this benchmark was doing a write of targeting at 1 gigabits per second. What you see is a reduction in the disk savings by 70% compared to no compression, and lower CPU overhead if you were going to do something similar with software-based compression. So this is using standard zlib. You're going to consume about 58% of the cores just to get their 23% down to 23% of the original size. So these percentages are of the original size. That's why compression off is 100. So this is basically with Quick Assist, you can drive down to 29% of the original size, and you're consuming 4.8% of the CPU. So essentially, you add 0.8% of the CPU, and you can drive it. You can save 70% of your disk space. Whereas you try to do that with software, as you can see, zlib is going to start to consume a lot of your cores. This is an 18-core system, up to 58% of your cores, and it'll drive it down to 23%. But that's your trade-off. Your trade-off is between ratio and performance. And again, LZO's quite good. It only takes up 9.2, but again, you're losing a lot of percentage. And if you're talking terabytes, that's a lot of space. We do similar work on RocksDB. So RocksDB uses its flush tables and compaction to do both decompression and then the read block. But they all go in through a standard compression library that supports zlib, bzip2, Snappy. What we did was we added our own compression library so that we could add parallelization. So that was kind of what I was talking about before, our parallel QAT zip. But we also have a shim that plugs in underneath zlib that adds Quick Assist capabilities, and it's behaviorally and functionally compliant with zlib. So you can take a zlib application, and with about only a handful of code line changes, you should be able to use Quick Assist through zlib. The performance won't be as good. Actually, in the context of this application, the performance is about comparable. But in some applications, depending on how they're written, the performance won't be quite as good as our parallel compression capability. But when you look here, so again, no compression, 100%. So the 3 lines are compression ratio, logical cores used of 64 logical cores, and database write throughput. You look at this, 100%, no compression. You're consuming 6.49 cores, and your write throughput is 978. You look at Quick Assist. Let's take Quick Assist at level 1 dynamic compression. Your throughput goes up to 18. You're consuming 10 cores, but your compaction goes down to 45% of the original size. Now, if you turn on, say, Snappy and LZ4 are probably the best for this use case. They're going to consume more cores. They're only getting 54 to 55. LZ4 is up to 19 cores. And then the write throughput is just underneath. So whatever way you slice it, if you want any level of compression, Quick Assist is giving you better. And then you have different levels and different parameters that you can tune depending on the data sets that you're actually compressing. And then finally, Hadoop. Hadoop, again, I'll go through this reasonably quickly, but Hadoop, where we hooked it in is as a codec into the Hadoop framework.
No, not reasonably quickly.
Because I'm eating into his time.
Getting anxious.
4 points, and I'll get straight to the numbers. You get so Hadoop is going to be measured in time. Hadoop is measured, I start a job here, when do I get an answer out here? So the really important thing that you want this is a MapReduce or a TerraSort benchmark. The thing you want is the answer, right? So how long did it take you to get the answer from when you kicked it off? So Snappy is kind of the best implementation that's in there today. You'll get about a 33%, depending on how you set up your containers and how many containers you get about a 33% just by putting quick assist compression in there. 33% improvement in time. In CPU cycles, you'll lower that down by about 9, in some cases 3, depending on how you do your container configuration. Again, you're getting the speed up here because of both the increased compression and the increased throughput.
You have a white paper link for this? This is something I need to look into.
I think it's right down there at the bottom,
Let's
isn't
go
it?
to performance. Okay. Thank you.
And if
No,
you
no,
don't
no,
find,
that's just the
no,
disclaimer.
that's just the disclaimer.
Like what?
So we have a white paper on this, and I will get you. I don't have the link in here. We're in the middle of writing it, basically,
Okay.
and we're going to publish it.
Thank you.
And then overall, from a compaction standpoint, you're reducing the data set by 12.5% for the TerraSort set of data that they use in this benchmark. And again, we're trying to upstream that codec. We're trying to get all that into the mainline. So again, you should be able to get all those components to do that. Summary.
Just go.
Key points. So as you can see, there's vast performance improvements from both security compression for both networking and storage that you can see with Quick Assist. We're trying to hit a large number of different applications. So we're trying to enable a bunch of different frameworks and do out different benchmarks. But as you can see, we've hit storage, Hadoop, file systems, databases, web servers. If you want to learn more, we have a website up for the Quick Assist kind of performance proofs and more information. That's more information on the IBM flash storage, so for the compression standpoint. And then there's general Quick Assist websites that you can go to get a lot more information. And then this was just the work that we're doing on OpenSSL 1.10 and how that mainlining is going to bring Quick Assist as a more easy to use type of acceleration.